Welcome to the first lecture in abstract algebra. The topics that we'll explore in this lecture include a review of facts about functions and countable sets. We're going to look at those infinite sets of numbers that are already familiar to you, and we'll be looking at algebraic and transcendental numbers. Okay, so I'm going to start this lecture by reminding you of some facts about functions and countable sets. I'm going to state these facts without proof, so if you are rusty on these topics or you want to see the proofs, I do develop them rigorously in lectures 5 and 6 in my series in general topology. So the first fact that we need to establish is a fact about composition of functions. So first, let f and g be functions such that the composition of f with g is defined. Then, if both functions f and g are injective, then the composition is injective. If both functions f and g are surjective, then the composition is surjective. And finally, if both functions f and g are bijective, then the composition is bijective. Okay? So next we'll state the definition for a countably infinite set. A given set B is countably infinite if and only if there exists a bijection which we'll call phi between the set B and the positive integers. That is, there is a one-to-one correspondence between this given set B and the set of positive integers. And as we'll see, the set of positive integers is identical to what we refer to as the natural numbers. But I'll point out at that time that there's a reason why we normally use the notation for positive integers rather than for the natural numbers. Okay, so new definition. What do we mean by a countable set? A set is countable if it is either finite or countably infinite. So a given set is countable if it is finite, which means that there's a terminating subset of the positive integers, starting with 1. Say a set that contains 10 elements. It is possible to list those elements in a given order that we choose and say this is the first element, this is the second element, and so on. In other words, we count them. In the case of a finite, rather an infinite set, it is impossible to actually list the elements as it is an infinite set. So the mathematical equivalent of counting those elements, that is putting them in a sequence and saying this is the first element, this is the second element, and so on, is to form a bijective function that maps the given set into the set of positive integers. And by doing so, we, in essence, create a sequence that lists the elements in any order we choose as the first element, second element, and so on, for an infinite set, and that being the set of positive integers. So again, a countable set is either finite or countably infinite, and so in principle, we can list each of its elements and say this is the first element, this is the second element, and so on. That is, we form a sequence with those elements. All right, so by contrast, a set that is not countable is uncountable. And so an infinite set that is not countable is called uncountable. Okay. So next we'll list some properties. First we'll give another way to identify uncountable sets, equivalent ways to identify countable sets rather. So let the set B be a non-empty set. Then the following are equivalent. If a set B is countable, then this is equivalent to the fact that there exists a surjection, which we'll call F, mapping the set of positive integers onto the given set B. So in other words, for every element in the set B, there exists at least one positive integer such that the function f maps that integer onto the given element in the set B. Every element in the set B is mapped onto by at least one element in the set of positive integers. This is also equivalent to the fact that there exists an injection, which we'll call G, mapping the set B into the set of positive integers. That is, every element in the set B is mapped into one element in the set of positive integers. So by definition, a set is countable if we can form a bijection between the set B and the set of positive integers, but with this theorem we have alternative methods to demonstrate that a given set is countable. We merely need to demonstrate that there exists a surjection mapping the positive integers onto the set, or that there exists an injection mapping the given set into the set of positive integers. So a very useful theorem that allows us to quickly establish whether or not a given set is countable. All right, so now we will state some properties of countable sets. First is that subsets of countable sets are countable. Now, if the given subset happens to be an infinite set, then this statement tells us that an infinite subset of a countable set is itself countably infinite. And that will be a very useful fact that we will use. Second, arbitrary intersections of countable sets are countable. Third, countable unions of countable sets are countable. So notice in particular that in this statement, the arbitrary union cannot be so arbitrary. It has to be a countable union of those countable sets, but any countable union of countable sets are countable. And finally, the final property that we'll discuss of countable sets is that finite products of countable sets are countable. Okay, so next we're going to start looking at the system of infinite sets of numbers that you are already familiar with, but we're going to dive into more of the set theoretic properties of these sets as we will be using them later as underlying sets and algebraic structures. So these statements that we just went through, again, a reminder of facts about functions and countable sets are going to be used in the context of algebraic structures where the underlying sets consist of infinite sets of numbers. Okay, so next we'll move on to those infinite sets of numbers. Okay, so we'll start with the natural numbers. The natural numbers are those numbers used to count. The symbol for the natural numbers is an ornate or blackboard bold letter N, and this is the set consisting of 1, 2, 3, and so on. So notice in particular the number 0 is not in the set of natural numbers. Okay, so next we'll define the integers. The integers consist of the number 0 along with positive and negative whole numbers, or correction, positive and negative natural numbers. The symbol for the integers is an ornate or blackboard bold letter Z. This comes from the German word Zahl or Zahlen, which means numbers. And again, it consists of the number 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Okay, so as a subset of the integers, the natural numbers are identical to the positive integers, and so we usually denote this way, the symbol for the integers with a superscript positive. Now the reason that we often make reference to the positive integers in definitions and theorems is that people tend to forget that the number 0 is not included in the natural numbers. And so by using the set of positive integers, positive meaning more than simply not negative, we don't make that mistake. And so often in definitions and theorems, you'll see reference to the set of positive integers rather than the set of natural numbers. But they are identical. Now, one of the obvious facts about the set of natural numbers is that it's countable. As the set of natural numbers is identical to the positive integers, we can define a function phi mapping the set of positive integers into itself by phi of n equals n. This is the identity function, and so it is a bijection, so it's certainly a bijection certainly exists, mapping the positive integers into itself, or in the natural numbers into the set of positive integers. And so the set of natural numbers, which again is identical to the set of positive integers, is countable. Now, shorthand notation for this is to show that the cardinality is the same as the cardinality of positive integers, and by convention, this cardinality, which is represented by absolute value signs, is not a finite number, but is given a transfinite number called aleph null. And any countable set has this same cardinality, that is the transfinite number aleph null. Okay? So next, we'll define the rational numbers. The rational numbers are ratios of integers. The symbol for the rational numbers is the ornate or blackboard bold letter Q. This symbol comes originally from the German, but now an English word, quotient, which roughly translates to ratio. And this is the ratio of integers m to n, where m and n are integers. And the second integer in the pair, or the denominator, if you want to think of this as a fraction, is not 0. Now, this representation of a rational number by a ratio of integers is not necessarily unique. For instance, the ratio of 1 to 4 can be expressed also as a ratio of 2 to 8, which is also expressed as a ratio of 4 to 16, and so on. So a rational number is a ratio of integers where the second integer in the pair, or the denominator, is not 0. And again, that representation of a rational number is not necessarily unique. Okay, so first we'll show that the entire set of integers is countable. And we'll state this as a lemma. So we define a function, which we'll call f, mapping the entire set of integers into the set of positive integers. And we'll define this by f of n is equal to 2n plus 1 if n is non-negative, and negative 2n if n is negative. So we're going to show that this function f is a injection, and so there are two cases to consider. So for every non-negative integer, suppose that f of non-negative integer m and n. Suppose that f of m n, f of m rather, is equal to f of n. Then, by the definition of the function, we have that 2m plus 1 is equal to 2n plus 1. And so 2m is equal to 2n. And so m is equal to n. So the assumption that f of m equals f of n implies that m equals n. And so the function f is injective. For non-negative integers. So now the second case, we look at all negative integers. And again, suppose that f of m is equal to f of n. Then by definition of the function, we have that negative 2 times m is equal to negative 2 times n. And so once again, m is equal to n. And so the assumption that f of m equals f of n leads to the conclusion that m is equal to n. And so the function f is injective for negative integers. And so as we have considered both cases of non-negative and negative integers, we see that the function f is injective. And again, this is a function mapping the entire set of integers into the set of positive integers. And so by the previous theorem that we developed before, we have an injection mapping a given set into the set of positive integers, and this is enough to establish the fact that the entire set of integers is countable.